Hello, everyone. Welcome to this session on complexity. The first speaker is Tommy Schuster, who's going to tell us about a polynomial time classical algorithm for noisy quantum circuits.
Hello, everyone. Thank you, Abhinav, for the introduction. So I'm Tommy Schuster, and today I'll tell you about a polynomial time classical algorithm for noisy quantum circuits. And this is joint work, first and foremost, with Chao Yen, as well as Shun Gao and Norman Yao. And so the motivation, the starting point, is a very familiar one to all of us. So we all dream of the ability to perform large and highly coherent quantum circuits and simulations. Yet, we know that in the near term, all quantum devices are inevitably impacted by noise. So as we are performing our circuit, our computation, noise events are happening in our system, and we have to figure out how to deal with that. And so in the absence of just improving the underlying noise rates, when confronting this challenge, one is faced with essentially three choices. The first is simply to restrict attention to very small circuits where we can essentially neglect the effect of noise. So in particular, if I take my circuit size to be less than roughly 1 over the noise rate, then with very high probability, no noise events occur in my circuit, and I can simulate a perfect ideal quantum system. At the same time, we would eventually like to simulate very large quantum circuits. And for that, one option is simply to wait for the advent of quantum error correction. And we know that eventually, with lots of progress and overhead, we'll be able to detect noise events as they occur and correct them such that we can effectively simulate an ideal quantum system without noise. At the same time, if I've done a lot of work to build a really high-quality quantum device right now, we don't really want to settle for small circuits, and we also don't want to wait for quantum error correction. And so what we actually do in practice is we perform very large quantum circuits in which we are well aware that noise is strongly influencing the outcome of our quantum computation. And so the field has spent a lot of effort over the last 5 to 10 years in trying to understand the behavior and potential applications of noisy quantum circuits. There's myriad research in this field on error mitigation, benchmarking, near-term algorithms, simulation, and quantum advantages. But there's sort of a fundamental question which hangs over all of this, which is how does noise affect the computational complexity of a quantum circuit? So this is clearly an important question for all of the applications on the previous slide. If a noisy quantum circuit can be classically simulated, then we essentially don't need to perform the circuit in the first place. We might as well just simulate it on our current classical computers. And so this is clearly an important question, and it's also a very old question. And so some of the seminal progress on answering this happened back in the early days of error correction in the 1990s. And so I'll quote just two sort of landmark results in that direction. So for one, we know that for noise rates below some threshold, it is possible to perform a highly structured circuit that does error correction, and in that way enables fault-tolerant quantum computation. And so we can, even in the presence of noise, perform highly complex quantum computations by doing error correction. On the other hand, it's also been established that for noise rates above a threshold, any quantum circuit can be classically simulated. And just as a ballpark figure, this threshold in these theorems is typically extremely large. It's, say, 20 or 40%. And so if you just stare at this, it kind of naively looks like this question of, what is the computational power of a noisy circuit is already answered. But then you kind of realize that these two extremes in these early results completely fail to capture the regimes of interest for current experiments, where in most cases we are not performing error correction, but at the same time, our noise rates are very, very good. They're not 40%, they're 1% or 0.1%. And so with this in mind, there's been a kind of flurry of recent works trying to understand the computational complexity of specific classes of quantum circuits at low noise rates. So restricting our attention to some specific class of circuit that we have some reason to care about, which rules out quantum error correction, and then asking, is that class of circuits easy or hard at low noise rates? And so I won't discuss, there's many interesting results in this direction, but I want to highlight just one that is particularly relevant for this talk, which concerns noisy random circuits. And so in particular, there's been this really nice pair of works, first by Shun Gao and Luming Duan, and later by Harnav et al. In 2023, which established that one can efficiently sample from the output of any noisy random circuit in polynomial time on a classical computer. And so this shows that in random quantum circuits, which we believe are very complex to sample from without noise, noise immediately spoils this quantum advantage, at least in an asymptotic scaling sense. And so if I want to really zoom out and just boil down this last slide onto 2 points, we know that on the one hand, we can perform very highly structured circuits which implement fault-tolerant quantum computation and can therefore realize complex quantum operations in the presence of noise. And on the other hand, these recent works establish that if our circuit has absolutely no structure at all, so if every gate in our circuit is drawn independently at random from SU4, then noise immediately renders the circuit classically simulable. And so the aim of this work and this talk is to address what happens in between. So for quantum circuits that have some structure, they're not completely random by any means, but maybe they don't have so much structure that we're performing error correction. How does noise affect the computational complexity of those circuits? And so before I get into this and our results, I'd like to just briefly review kind of a key tool for how we understand noise and complexity in these circuits. And so this is a tool that was really introduced in the context of these noisy random circuit papers by Gao Duan and Harnav et al. And this tool goes by the name of polypath methods, although this name was coined after the methods were developed. And it begins from a very simple starting point. So imagine I'm interested in computing some observable, O, and I'm interested in computing its expectation value after a circuit C has been applied to some state rho. So what I'm gonna do is I'm gonna take this expectation value and I'm gonna write it as a sum over paths of poly operators over space and time. So in particular, I start at the final time step. I have my operator O, and I write it in the poly basis. Then I evolve each of these poly operators through the last layer of my circuit. Then I decompose in the poly basis again, and then I evolve again and decompose again, and so on. And in this way, I form an effective kind of Feynman path integral for this expectation value in operator space. And the key observation of these works was that in noisy circuits, the dominant polypaths, the ones with the largest contributions to my expectation value, happen to be very sparse in space and time. So their weight, which is equal to the number of non-identity components, is very small. And the reason this is true is actually super simple. It's just because if I just act a single noise channel on a poly operator at a given time step, the noise channel damps the amplitude of that poly operator exponentially in its weight, like e to the minus gamma weight. And so very high weight poly operators storing very non-local information are very quickly and strongly damped by noise. And so with this broad idea, these works showed that you can classically simulate a noisy random circuit in polynomial time by simply simulating only the low weight poly paths. And the key step in this proof is to show that the error due to the truncated high weight poly paths is very small. And from that, it turns out it's relatively easy to show that keeping track of all the low weight paths can be done efficiently. And so, so far, this intuition all sounds very broad in general. But it turns out that when we're bounding this truncation error due to high weight paths, it's a very tricky topic. And the reason is that there are exponentially many high weight poly operators, 4 to the n. And so even though the contribution of each one might be somewhat small, e to the minus gamma n, their total contribution could still be very large. And it's a very tricky business in general to bound this error. And to get over this, all existing rigorous polypath methods, whether for classical simulation or other purposes, essentially restrict attention to random circuits. in which every gate is independently random. And they then leverage a special property of random circuits, which says that in a random circuit, polypaths behave incoherently on average. So if I have a poly operator that's the same at some time step, and then differs at some later time steps, and then reconnects at a later time, in a random circuit, on average, they do not coherently interfere. They might instance to instance, but on average, they do not. And in a way, this allows one to bound average properties of these circuits via a mapping to a classical Markov process, which enables very simple bounds on this error. The details are not too important. And so at a somewhat technical level, a question that we might ask is, do quantum coherences in operator space, which generically arise in any non-random quantum circuit, do these fundamentally break polypath approaches? Or maybe, do we just need to develop a better way to understand and bound the errors for these methods? And so now I'll get to where we come into this story. So in our paper, we provide the first rigorous application of polypath methods outside of random circuits. And in so doing, we prove that any noisy quantum circuit is classically simulable on most initial states. And so in slightly more detail, what we show is as follows. So for any observable O and any noisy quantum circuit C, we provide a classical algorithm to compute the expectation value of O after C is applied to a state rho. And our algorithm succeeds with a small average error over input states drawn from any complete basis. So for example, the computational basis states. So you give me a computational basis state, I run my algorithm, I compute some expectation value, and my expectation value is correct on average with a very, very small error. Another way to frame it is with very high probability over the input state you've given me, my algorithm is accurate. But it might fail on some very small fraction of input states. And our algorithm runs in either polynomial time or quasi-polynomial time in the parameters n, the number of qubits, d, the depth of the circuit, and epsilon, the desired error. The precise runtime depends on the noise model of interest. And I would like to note that the runtime is exponential in the inverse noise rate. And this is fundamental, because I can always restrict attention to a small circuit of size roughly 1 over the inverse noise rate, in which case we'd expect the complexity to grow exponentially in that system size. I'd also like to just briefly remark that this restriction to almost any input state, so ensembles of input states, is also fundamental, because we're already allowing any arbitrary quantum circuit. And so if I also allowed you any arbitrary input state, you could simply perform quantum error correction. And then we know that we can perform complex quantum operations. And so I'd like to now describe our algorithms, and we in fact provide two. And the two algorithms are very similar in spirit, but slightly suited to different noise models. So our first algorithm is actually the same algorithm that appeared in this work by Gao and Duan and Aharonov et al. And the algorithm estimates an expectation value by simulating all polypaths with a sort of space-time weight less than some threshold L that we choose. So I take the path, I compute the sum of its weights over every time step, and I only keep that path if its summed weight is less than L. And we prove that even outside of random circuits, so in any noisy quantum circuit, on average over input states, this algorithm succeeds with a polynomial runtime. There is a somewhat technical condition on the class of circuits we consider, which is we consider noisy circuits without fresh qubits. If you don't know what a fresh qubit is, don't worry, it's just a technical restriction, and it's kind of the common noise model that is studied in most works on noisy random circuits. We also provide a second algorithm, which I'll call a step-by-step truncation algorithm, in which we simulate all polypaths that have a weight less than L at every time step t. So not the summed weight, but each individual weight is less than L. And you can think of this as I just evolve my operator in time, and at each time step, I check if it has any support above some weight L. If it does, I throw it away. Then I evolve it. Then I check if it has any new support above weight L. If it does, I throw it away, and so on. And we show that this algorithm has a quasi-polynomial runtime. And this algorithm actually applies to noisy circuits with or without fresh qubits. And this inclusion of fresh qubits, again, is a somewhat technical restriction, but it is also a key ingredient for quantum error correction. So it's kind of a necessary ingredient in order to directly compare the setting of our results to those in theorems of fault tolerance. So I'll now just very briefly describe our proof techniques. So as I think has been clear, our algorithms are very simple, and they're very similar to algorithms that have been studied in numerous previous works. And so the real innovations in our paper are in how we bound the errors in these algorithms. And in particular, as I discussed earlier, the key challenge in bounding the error is in bounding the effects of coherences from lots, exponentially many, high-weight Pauli operators, which might coherently interfere to give a large error. And so to bound this error in the space-time truncation algorithm, we organize the exponentially many Pauli paths into a tree. And roughly speaking, our classical algorithm, I should describe the tree, sorry, the layers of the tree correspond to the layers of the circuit, and each branch at each layer corresponds to all Pauli paths with a weight, some weight W at that layer. And so with this, our classical algorithm can be viewed as simply snipping the branches of this tree as soon as their total weight surpasses this threshold L. And what we show is just using the orthogonality of the Pauli operators, each individual snip in this tree has some small overall error. And so bounding the total error of our algorithm boils down to just counting the total number of snips that I make. Turns out this is an easy problem to count. There are L choose D total truncations, and so we get a total truncation error less than L choose D times this exponential factor. And from this, I won't describe it in detail here, but it is very straightforward to go from this error bound to the polynomial runtime of our algorithm. I'll now very briefly discuss how we bound the error in this step-by-step truncation algorithm. As a very brief comment, the step-by-step truncation algorithm is much simpler and it's much easier to bound the error in. So in general, if you are hoping a polypath method might apply to your problem, I would recommend maybe starting with this algorithm where it's much easier to form simple bounds and then trying to improve things from there. In our setting, the reason we consider this step-by-step truncation algorithm is to incorporate circuits that can allow fresh qubits. So qubits that were unaffected by noise up to some point, which we then insert into the middle of our quantum circuit. And at a technical level, we do this by allowing circuits where the noise only occurs in non-identity gates. And then to bound the truncation error, we prove a very general bound on something called the weight distribution of any time-evolved operator in any quantum circuit with noisy gates. And I'll skip most of the details here for sake of time, but I'd like to just mention that the proof of this bound is surprisingly subtle, and we developed some nice techniques for bounding the flow of operator weight over time, which allow us to achieve this tight bound on the error. And I'll just briefly comment that we can also extend our algorithms to sampling for circuits that anti-concentrate, also for circuits where noise occurs only in the non-Clifford gates, also to random quantum circuits with non-unital noise, and finally to any noisy quantum circuit on any highly mixed initial state. And so in particular, in this last point, we prove that noisy DQC1 is in BPP. So with my remaining time, I'd just like to very briefly go over a few implications of our results. And I'd like to start by just giving kind of my personal interpretation of what our results say and do not say. And I think the most important thing to say is that our results do not by any means rule out quantum advantage in noisy or NISQ experiments. Rather, they simply show that this advantage is limited both by the number of qubits and by the noise rate of the experiment. I think this is fairly intuitive to many of us who have worked with noisy circuits, but it's nice to establish it on much more general and rigorous grounds. And one remark I'd like to make is that our work shows this is not some special weakness of random circuits or random circuit sampling, but rather a fairly general feature of a large class of quantum circuits without error correction. And so I'd like to dive into one slightly different, more specific implication as just the last part of this talk. And that concerns the overhead of noise mitigation strategies. So I haven't discussed noise mitigation at all so far in this talk, but broadly, it refers to a set of strategies that seek to recover properties of ideal circuits from experiments on noisy circuits. And there's lots of different methods, but there's some very nice recent works that show that for worst-case circuits, any noise mitigation strategy always requires what's called a weakly exponential overhead. So an overhead that grows like e to the gamma n. So it's exponential in the number of qubits, but with a very small exponent proportional to the noise rate. And so sometimes people have seen these results, and I think people interpret this as saying that error mitigation always requires this very large overhead. But this is very much not the case. This is a worst case result where certain circuits can require this very large overhead. And in fact, you can very easily convince yourself with very simple examples that this overhead is not required for every circuit or mitigation strategy. And so in this line of thinking, even several recent works have tried to look for circuits that are surprisingly easy to error mitigate, that can be mitigated with much fewer samples than this naive bound. And this is, a reasonable thing to pursue while we're looking for reliable, large-scale, near-term simulations. And unfortunately, our results pour a bit of cold water on this pursuit. So our results prove that a weakly exponential overhead for quantum error mitigation is necessary for any classically complex quantum circuit. And the reason is very, very simple. So suppose I had, say, a polynomial-time method to error mitigate a noisy circuit. Well, I've just shown you today a polynomial-time classical algorithm to simulate noisy circuits. So I could use my classical algorithm to simulate the noisy circuit and use my polynomial-time error mitigation to then simulate the ideal circuit. So it's just a very, very simple and straightforward corollary of our results. And as with everything I've discussed so far, this holds for any noisy circuit on most input states. And so I think at a broad level, what this tells us is that we should take a cautious approach to searching for circuits that are surprisingly easy to error mitigate. Because oftentimes, the same properties that are making a circuit easier to error mitigate than we might expect happen to be properties that also make the circuit easier to classically simulate. And in more of a physical picture, this is because circuits that are easy to error mitigate have expectation values that are dominated by low-weight polypaths, which are very weakly affected by error. And this also makes these circuits efficient to simulate with these polypath algorithms. On the other hand, if we want a circuit that is hard to simulate with these algorithms, then this circuit will necessarily have very high-weight polypaths. And these are very strongly affected by noise, which will make it harder to error mitigate. So I'd like to leave some open questions on the board. In the interest of time, I won't go through each of them. And I'll open up to questions from the audience now.
Yeah, we have time for one or two quick questions. Let's go with. Please wait for the mic.
Yeah, so you mentioned that your sampler works for non-unital noise and random circuits, but is that for a specific model of non-unital noise? Because generically, I don't think that
So
holds,
it was not sampling. It was expectation values in random circuits with non-unital noise.
I see.
And we prove it for a specific non-unital noise model, but there's a much more recent work by folks, I forget all of the authors, which expands it to any, I think, single qubit non-unital noise channel.
So can you comment on the complexity of sampling with non-unital noise right now?
I don't know. It's an interesting question.
Okay, we can do one more there. Okay, yeah, thanks. Let's thank the speaker again.